Hello everyone, welcome to the very first exam prep recording session. So again, the purpose of these videos is to help students who weren't able to go to the actual discussion for whatever reason to be able to follow along with problems as I do them through this video and be able to kind of catch up on things that they might have missed. So my name is Sherman. I'm one of the TAs that's in charge of making these videos. So let's go ahead and get started. This first discussion of exam prep is based on search. And so let's just go ahead and dive right into this first problem. So it is training day for Pac-babies, and the situation is that there's K Pac-babies, and each of them needs to, so there's K Pac-babies, so the grid might look something like this. There's P1, P2, P3, and each Pac-baby has a goal, G1, G2, G3. And the goal is for each of the Pac-babies to return to their dads, but along the way they have to collectively be able to collect all the dots that are possibly in the maze. So let's go ahead and try to define a minimal state representation, state space representation for this problem so that we have enough information but not too much encoded in our state so that we can solve this problem. So some of the things we might need in this problem, we definitely need the position of the Pac-babies. And we also need something else, which is the position of the foods. So, sorry. So these booleans will indicate the presence of food. And we also need the position of the Pac-babies. So this is everything we need. So the position of the dads is known, the position of the walls is known, so we don't need to encode that information. So next, let's go ahead and take a look at how, so this is Boolean, sorry. Now let's take a look at how large the state space is. So now we need to consider what are the positions of the Pac-babies and how many different positions could the Pac-babies take in conjunction. So each Pac-baby, if the way I like to think about this is if there's one Pac-baby, this one Pac-baby can take m times n. So this will be m, this will be n. So one Pac-baby can take a position out of mn squares. If there's two Pac-babies, then the first Pac-baby can take mn spaces, and the second Pac-baby can take another mn spaces. If there's three, then we multiply mn again because the third Pac-baby can also take one of any of the mn spaces. And this, if you follow this pattern, this multiplies out to, with the kth one, so there should be a total of k of these. So the total number of places that the Pac-babies could reside, like the locations of the Pac-babies, is mn to the k. And so this is positions. And the next thing we have to consider is the booleans of the food positions. So if there's mn food positions and either of these can exist, or each of these food could either still be present or it could not be present, then we look at basically each bit of this Boolean representation could either be true or false. And since there's a possible total of mn food pieces, then we raise that, we exponentiate that 2 to the power of mn, because each of the Booleans could be true or false. So this would be our state space size. This left term could correspond to the position of the Pac-babies, and this right one corresponds to the food. Okay, now let's take a look at the maximum branching factor for this problem. So what is maximum branching factor? Maximum branching factor is essentially from one state, like this, how many different states can this lead to? Depending on the action taken the action taken in conjunction of all the different Pac-babies. So each Pac-baby has a choice of 4 actions. So the first Pac-baby has a choice of 4 actions. The second Pac-baby has a choice of 4 more actions. And if there's 2 Pac-babies, then together in conjunction, they have 16 different actions that they could be taking. So if there's k Pac-babies, then we need to multiply this up to k times, and this will be equal to 4 to the k. So it's going to be 4 to the k. Okay, and now let's go ahead and talk about part D. So now we're going to be examining a bunch of different heuristics, and we want to see which one of these heuristics is admissible for this problem. So just a reminder, admissible means that it never overestimates the true optimal distance to the goal. So let's take a look at H sub A. So these kind of look intimidating to start, but let's just go ahead and try to reason about them one step at a time, and hopefully it starts to make a little bit more sense. So let's take a look at what H sub A really means. So H sub A is the sum from 1 to k, the Manhattan distance of each Pac-Man to its goal, or each Pac-Man to its dad, and then we divide that by k. So this is going to be admissible. And the reason for that is because you can think of this top term as if we have like a grid right here. Actually, let's just refer to this previous grid. If we have this grid right here, we're going to sum the distance for each Pac-Man to its goal. And that's going to represent the total amount of distance that each Pac-Man has to travel to their goal. This is the total distance that Pac-Mans have to travel to their goal. And in each time step, and each step of the game, each Pac-Man can get at most one step closer to their dads. And since we know that each Pac-Man must eventually travel to their dads, this is the minimum distance, total distance that all the Pac-Mans have to travel together. And since in each time step they can only reduce this total distance by at most k, since there's each Pac-baby can get at most one step closer, and there's at most and there's k Pac-babies, then they can reduce that number, the total distance, by at most k every step. And so this therefore must be an underestimate, because they can't reduce it by more than k every step. So it cannot overestimate the total number of time steps to get to the goal in the most optimal case. Okay, now let's talk about H sub B. So H sub B represents the, we're going to take a max over all the Pac-Man, and we're going to look at the Manhattan distance between each Pac-Man and its dad. So this is also going to be admissible, because if we have some case like this, where we have P1 is like 100 distance from its dad, and P2 is like 10 distance from its dad, we know that Pac-Man 1, we have to, even though the Pac-Man can move together, like one step together in every time step, we have to wait for P1 to get to its dad at least, right? Because we know that we have to be waiting for each Pac-Man to get to its dad. And so therefore, the farthest Pac-Man from its dad is kind of like a lower bound on the amount of time we have to wait. Because we have to wait for all Pac-Man to get to their dads. So we have to wait for the farthest Pac-Man from its dad. So this is also going to be admissible. This cannot possibly overestimate the true cost, true optimal cost. So next, let's talk about the third heuristic, part C. So let's take a look at this. So this is a pretty intimidating expression, but let's try to break it down a little bit. So this is, we're taking a max over all the food, and we're getting the Manhattan distance from each Pac-Man to that food. So, and then we're taking a max over all the Pac-Man. So this is definitely a little bit confusing, but the way I like to think about this is to first understand what's on the inside maximization, and then once we understand what that is, we can understand what's on the outside with conjunction with the one on the inside. So let's first take a look at the inside. So we're going to take a max over all the food. So let's just fix P sub I for, very quickly. So P sub I is just any arbitrary Pac-Man. And so let's just go ahead and fix that. And we're basically going to take a max over all the food to find the food that's the farthest away from that Pac-Man. So this inner part is the food that's the farthest from that Pac-Man. And now we're going to look over all the different Pac-Man. So we're going to take a look at the farthest food from any Pac-Man. So we're going to look at all the Pac-Man, look at which food is farthest from each of them, and basically take what's the biggest out of that. So if we have like P1 here, P2 here, let me draw this grid, and then we have G1 here, G2 here, then we're going to realize that if there's a food here, and there's just like one food there, then the farthest food from P1 is just going to be this, it's just going to be 1, because the farthest food from P1 is just right here. The farthest food from P2 is going to be 1, 2, 3. So, and then we're going to take a max over that. So biggest out of 1 and 3 is going to be 3. So the farthest food from any Pac-Man is going to be P2 and this one piece of food. And but this is obviously not admissible because we can solve this problem quicker than that. We just have P1 immediately go to the goal. We have P2 immediately go to its goal. And thus, we can solve this game in 2 steps. So what was the issue here? Intuitively, the problem here is that it's not the case that P2 is necessarily picking up this piece on the way to the goal. It doesn't make sense for the absolute farthest Pac-Man from its food, the absolute farthest food from any Pac-Man, like P2 doesn't necessarily have to be picking up that piece on the way to the goal. In fact, it probably wouldn't. It intuitively makes sense that it doesn't have to pick up that piece because it is literally the farthest piece from P2. So this is not admissible for that reason. Let's go ahead and move on to part D. So part D is very similar. Instead of looking at the max of every there's going to be a minimum on the inside instead of a maximum. So now instead of taking a look at the farthest food from every Pac-Man, we're going to be looking at the closest food to every Pac-Man. And then we're going to take a max over that. So basically, again, P1 is going to find the closest food, which is this. P2 is going to find the closest food, which is also that. And then we're going to take the biggest out of that. So again, the heuristic here would be 3. However, we can solve this game in 2 steps. So this, again, is not admissible. And the reason, again, is because it doesn't make sense for Pac-Man 2 to necessarily have to be getting this piece on the way to the goal. Since we're taking a max over all the closest foods, or we're taking a max over all the Pac-Man and their closest foods, it doesn't necessarily have to be the case that P2 is getting any food at all. So therefore, we can solve this game even faster than in 3 steps, and this is not admissible using this counterexample. So now let's look at H sub G, or H sub E. So now we're taking a minimum. We're finding the closest food to every Pac-Man. And so this is the closest food to every Pac-Man again. And then we're finding the Pac-Man, because we're iterating over the Pac-Mans, to find the Pac-Man that has the closest food to it relative to any other Pac-Man. So this is the Pac-Man that has the closest food to it compared to any other Pac-Man in the game. And this is going to be admissible. And the reason for that is this is essentially saying that this is referencing like the absolute closest food to any Pac-Man. And some Pac-Man is going to have to get that piece of food. And because some Pac-Man has to get that food eventually, the closest Pac-Man to it is like the distance that the closest one travels to the closest piece of food is at least the amount of time steps we need to solve the problem, because some Pac-Man has to get the food, and the closest Pac-Man, the distance from that Pac-Man to that piece of food is going to be a lower bound, because some Pac-Man has to get it, and the closest one is a lower bound. It's not the case that the closest Pac-Man necessarily has to get that piece of food, but it is a lower bound, just that distance at least. So this is admissible because some Pac-Man has to get that food. So now let's look at H sub F. H sub F is now iterating through the Pac-Man on the inside. So it's basically saying for each piece of food, so just given a piece of food, what is the absolute farthest Pac-Man from that piece of food? So this is, the inside is saying what is the farthest Pac-Man from that piece of food, and then we're going to iterate through all the food, and we're going to find which food yields the smallest value, or which food has the smallest farthest Pac-Man from itself. Yeah. So let me continue this example. So if there's 2 food here, the farthest food, or the farthest Pac-man from this food right here is P2, which is 3. And the farthest food from this Pac-man is P1. Or sorry, the farthest Pac-man from this food is P1. And so basically this is 3 right here, and then this is also 3. So we're taking a min over 3 and 3. And thus the answer, our heuristic here would be 3, which again is an overestimate of the true optimal goal. And so intuitively, the case why this is not admissible is because since we're looking at the farthest Pac-man from every food, and then we're taking like the food that has like that smallest value. It's not necessarily the case. In fact, it doesn't really make sense to even assume that the Pac-man that's the farthest from that piece of food is necessarily the one that's going to get it. Like for this piece of food, we can't assume that P2 is getting it, and for this piece of food, we can't assume that P1 is getting it. And in fact, the optimal goal would just be for them to both run it down to their parents. So this is not admissible. Okay, let's go ahead and move on to part E. So now we suppose that some of the squares are flooded with water, and in the flooded squares, it takes 2 time steps to travel through the square instead of 1. Except in this case, we don't actually know which squares are flooded and which aren't until one of the Pac-babies enters them. And as soon as one Pac-baby enters them, everyone else knows about this fact, and the state, whether the square is wet or not is known. So let's go ahead and define a minimum space of belief states for this problem. So before I define what a belief state is, let's define what a physical state is. So physical state is an actual possible configuration of the board. So an example of a physical state, if there's like a 2x2 grid, is, for example, dry, 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 right? So this is like one actual possible configuration of the board, and like one possible actual true configuration of how the board is set up. However, in this case, in a lot of cases, we don't know what the true configurations are, so we need something that's called a belief state. So belief state is a set of physical states. So I'll give you a couple examples of what a belief state might look like. A belief state could look like, so everything's dry. This is one physical state. So this is one possible belief state, and what this represents is we absolutely know that every space is dry. Here's another belief state. Dry, 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 and wet, 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 wet. So this is another belief state. So and this belief state contains 2 physical states inside of it. And what this represents is we believe that the true configuration could be one of these 2, could be one or the either. And the reason why belief states look like this is because when we're playing this game, we don't know what the true configuration of the board is. We don't know what the true physical state is, so we need to keep kind of like a set of possible physical states. So a belief state is a set of physical states that we think are possible. And let's go ahead and define like what the space size is. So a physical state has mn bits. Okay. So how many different possible physical states are there? It's going to be, so this is mn bits for each, this is a physical state. And since each bit in the physical state can either be wet or dry, we're going to raise this to the power of 2, and it's going to be 2 to the mn. So this is the total number of possible physical states. It's going to be this. So the possible number of physical states is 2 to the mn because each bit could either be true or false, or wet or dry. And so now we want to look at the space of belief states. So this is going to be even massively larger than what we already have. So remember that the belief states is a set of the physical states. So how many physical states are there? There's 2 to the mn. So how many different ways can we take a subset of the physical states? So this is something called the power set. So if there's 2 to the mn physical states, the number of ways we can take subsets of the physical state set is 2 to the power of 2 to the mn. So this is our final answer. Belief space size. Okay, and yes, there's another way we could look at this. So this is like the kind of the canonical definition that we're looking with, but we can find like another space of belief states that might be potentially smaller. Another way we can think about this problem is each state can either be wet, or sorry, each grid space can either be wet, dry, or unknown. And so our belief state could simply just be something like this, where each grid space is either W, dry, or like a question mark. And this would encapsulate everything we need to know about, in this case, about whether of the uncertainty of the problem. So we know that this space is W, we know that this space is D, and we don't know what these two are. So this representation also works. So since there's 3 different possible values in our matrix, this would be 3 to the mn. So this is the number of possible belief states. So this is an alternative answer that also works. So how many possible configurations are there in the initial belief state? So we already talked about this already. If there's mn, so we're going to be referring to the first answer that I talked about. So if there's mn bits for whether it's dry or wet, it's just basically, so mn bits. And in this case, we don't know anything about the start state, right? So we don't know anything about like whether something's dry or wet. Then each one can either be dry or wet. So we're gonna do 2 to the mn, since every bit can either be dry or wet, since we don't know what it is at this in this point in time. So this is the total number of different configurations there are of the board. So this is basically how many physical states are in our initial belief state before we get any percepts of like wetness. So given the current belief states, how many belief states can be reached in a single step? In this case, like before, we have 4 to the k different actions for the Pac-man. Okay, so this is the branching factor for just the movement of Pac-mans. And we also have to multiply something extra, because we don't know if we'll land on a wet space or a dry space. So each Pac-man will experience either wet or dry at most, or they see something that they've already seen, but this is the maximum number of belief states. So, or the maximum branching factor of this problem. And in this case, we can either see dry or wet. And so each Pac-man will basically contribute a factor of 2. And since there's k Pac-man, we multiply that together to get 2 to the k, and then this simplifies to 8 to the k. So again, I'll repeat that one more time. Each Pac-man moves a space up to 4, and they receive either a wet or a dry percept, which changes the belief state that we result at. Okay, so let's go ahead and jump into question 2 for search. So this is a Rubik's Cube problem where there are a total of 4.3 times 10 to the 19th possible configurations. And it's very important to know that any configuration can be solved in 20 moves or less. And we're trying to basically solve a Rubik's Cube. And since there are 4.3 times 10 to the 19th possible configurations, we have a maximum number of states of that number. And each edge has cost 1. So moving the cube just costs 1 step for every turn. And it does contain cycles, and intuitively this should make sense because if we turn the cube like 4 times, it comes back to itself. And we can make 27 moves from each state, so the branching factor is 27. And since each configuration can be solved in 20 moves or less, the heuristic that is optimal is going to be less than or equal to 20, because if it's more than 20, it's inadmissible, because that would be an overestimate of the number of steps it takes to solve the cube. So we're just going to go through this problem, and we're going to see which of these we're going to take a look at the best case and the worst case for each of these different kinds of search. And it's very important to note that 27 to the 20 is much larger than the actual number of states in the graph itself. So the number of configurations of Rubik's cubes is much less than 27 to the 20. And 27 to the 20 should be kind of like a familiar number to you. It definitely didn't come out of nowhere. And we're going to go ahead and see where this comes from and why it might be useful that this is much larger than that. So for DFS tree search, what is the best case? So if this is the start, this is the goal. What we want to do is run DFS tree search. In the best case, we get super, super lucky and we just find the exact correct path from S to G instantly, and we get a best case of 20. In the worst case, it's actually infinite because we're doing DFS tree search, and we know that tree search is incomplete. DFS tree search is incomplete, and we can easily get stuck in some sort of cycle here. I'm sorry, I'm not good with the pen. We can get stuck in a cycle in the worst case, and this could never finish. So for DFS graph search, this time we can't revisit the same states, and we know that the graph search is more complete is complete this time because we cannot revisit the same states, and we know that there's a limited number of states in the Rubik's Cube problem. So SG. In the best case, again, we just go right to the goal. In the worst case, we can't get stuck in a cycle because we can't revisit the same states again. However, in the worst case, we can be searching in the complete wrong direction. We have no guarantee of when we find the goal, since DFS is just randomly looking around, just kind of like searching the deepest path first. And so in the worst case, we're looking at every single node in the graph. And the number of nodes in the graph, again, is 4.3 times 10 to the 19th. For BFS tree search, so BFS, again, it's going to search uniformly with respect to distance from the start in the number of steps. So again, here's this. So in the best case, we are going to be searching 27 to the 20. And the reason for that is because it's going to be uniformly searching from the start in a circle, and it is going to possibly revisit states, and every single kind of like circle here is going to be a factor of 27 times bigger because the branching factor is of size 27. So in tree search, since we can revisit states again, and every single loop that I'm drawing here, and there's 20 of these loops since G is possibly 20 steps away, then we're going to be we're going to be searching at best 27 to the 20th because G is 20 steps away, and we're going to have to search all these loops uniformly until we get to the goal, and there's no way around that. Our best case is 27 to the 20. In the worst case, it's going to be exactly the same, 27 to the 20. For a very similar reason, it doesn't really matter how lucky we get that much in this case because it's just going to have to search uniformly anyways. So it doesn't matter how lucky we get. In BFS graph search, it's going to be very, very similar, except now we can't revisit the same states. So in the best case, again, we have to search nearly the entire graph, approximately this much, because S and G have 20 apart, and we know that the entire graph itself is 20 wide, or the farthest point from any point in the graph to any other point is 20. So therefore, we're searching kind of like in a magnitude of the entire graph. We're going to need like 20 of these uniform loops in order to find the goal, and that's approximately the size of our entire graph anyways. So we're going to be searching we're going to be searching the entire graph because the goal is 20 steps away, and the graph is 20 steps wide. So in both the best case and the worst case, we have a similar performance. So you can see that BFS is a very consistent type of search because it searches uniformly. And so now we're going to be taking a look at A-star tree search with the perfect heuristic. So if we have a perfect heuristic, if we have from S to G, then it's going to be very easy for us to be able to find the goal. Like assuming that there's no other paths that are also optimal, then we should be able to find the goal in just 20 steps, like instantly, because the heuristic will guide us perfectly and be able to elucidate to us what is the perfect path from S to G. So this case would be just 20. So next we're going to take a look at A-star tree search with a bad heuristic. So this bad heuristic, intuitively, if we have like an S and a G, it's going to be saying that if we get closer to G, it's going to be like a bad thing. We're going to see like getting closer to G because it's 20 minus the actual distance to the goal. So if we get closer to G, our heuristic is actually going to go up. So it's going to encourage us to go in the wrong direction, to search in the wrong direction first. And first, let's take a look at, it's not infinity because in the worst case, it would not be infinity because this would eventually have to terminate and find the goal, because the only way it could go to infinity is if it found an infinite loop and continue to search along that loop infinitely. But it can't do that because if you go in a loop, that will eventually, going in the loop, taking steps along that cycle is going to incur a step cost, and eventually that step cost is going to exceed it's going to prevent it from continuing to look in that cycle, and it's going to eventually have to look elsewhere. So that's kind of like a very intuitive sense of why it can never get stuck in a cycle, just because that would generate an infinite amount of like path cost to stay in that cycle. So it can't stay in that cycle. So eventually it will find the goal. However, precisely, it'll have to search very, very far. It'll have to search like distances of 20 away before it can even start going to the goal, because the heuristic is 20 minus the optimal, then it'll have to search, it'll have to like have gotten 20 away from the goal in order to kind of balance out with the nodes that are going towards the goal. I know that's a little bit of a hacky explanation, but the closest thing to that is going to be 27 to the 20. And actually, more precisely, it should be something closer to 27 to the 40, because it might have to search a circle of size 40 instead of 20, since it is subtracting 20, or we're basically getting like a minus 20 in our heuristic. So we're going to have to search like a circle around our start of size 40. I think there's a good explanation of this on Piazza by Henry. So if you're still confused about this, definitely look that up. So A-star graph search with the perfect heuristic, again, it's going to be 20. So not too much to say about that. Perfect heuristic, in the best case, it just helps you find the path perfectly. A-star graph search with a bad heuristic. In this case, again, it can't be infinite. And in this case, it can't, normally would be 27 to the 20. However, we can't visit the same states again twice. And we know that the number of states is going to be 4.3 times 10 to the 19th. And in the worst case, it just visits every single state. So in the worst case, we visit every single state. And this is because 4.3 times 10 to the 19 is smaller than 27 to the 20. And if we didn't have the guarantee that we couldn't visit the same state twice, like in tree search, it would be 27 to the 20 or 27 to the 40. However, in this case, at worst, all it can do is search the entire graph, which is much better than the worst case of tree search. So now let's go ahead and talk about a limited A-star graph search. So limited A-star graph search is the same as normal A-star graph search, except we have an argument W, and this W is basically limiting the size of our fringe. So if our fringe looks something like this, with a bunch of nodes inside, it can't exceed this size W, and if it ever does, we're just going to cut off everything after that. So the first question is, for a positive W, is A-star graph search, limited A-star graph search is complete? And let's go ahead and draw a simple example. This is the start, this is the goal, this is some random other node, A. Let's say that W is equal to 1. Okay, and in this case, we're going to draw this such that, this is 5 and this is 10. Okay, so when we first take a look at S, we're going to add 2 nodes to our priority queue, A and G. And this has a value 5, and this has a value of 10. Let's just say that our heuristic is a 0 heuristic for now, so we're just doing uniform cost search. And in this case, since W is 1, we're going to cut off the goal. And since we cut off the goal, we have literally no way of ever seeing the goal. So we'll just go to A, and we'll never find G. So since we never find the goal in this case, it is not complete. So just take a look at these like simple examples, and these simple examples should help you elucidate why cutting off our fringe is something that we can't do if we ever want to guarantee that we can solve the problem. Is it optimal? No, because we can't even find the path sometimes. Find the smallest value of W such that this algorithm is equivalent to a normal A-star graph search. So the smallest amount of W is, conceptually, we cannot cut off any nodes in our fringe. Our fringe has to accept every single node that we're putting in it. We can never cut anything off because it's possible that any node could be useful in our path to the final goal. And so the smallest value of W has to be able to encompass every single node inside the graph. So this is going to be, W has to be at least the state space size. Okay, now let's go ahead and move on to Pac-Man's life. So there's a maze of height m by n, and there's f food pellets. Pac-Man can move up, down, left, right, and he wants to pick up all the food pellets in the maze, but he can only move up twice. Let's find a minimal state space representation. So let's go ahead and think about what is important to solve this question. What's important for us to encode in our state? So we're going to definitely need Pac-Man's position. And this is going to be, there's going to be mn possibilities. There's going to be m times n possibilities for Pac-Man's position. Next, we need to know the food pellets, if they exist or not. So since we know where the food pellets are, and we know that there's f of them, we have a list of food pellets. And this list is basically, can be like a Boolean vector, for example, of food pellets. If it's true, then the food pellet still exists. If not, then it's gone. So this is going to be 2 to the f, because each food pellet could either be still existing or not. So, sorry, I wrote this in the wrong place. So this would be food times 2 to the f. And lastly, there's one kind of hitch in this problem, which is that Pac-Man can only move north at most 2 times. So we're going to have to keep track of how many times Pac-Man has moved north. Let's call it north history, which is how many times Pac-Man's already moved north. So Pac-Man can either have moved north between 0, 1, and 2 times. And so since there's 3 choices here, we'll multiply that by 3. So this is our total space, the state space size. So now Pac-Man's lost in the maze and he doesn't know his location. However, he still wants to visit every single square. And now we want to be able to find a sequence of actions that he will visit every single square no matter where he starts. So let's go ahead and take a look at a minimal state space for this problem. So before we start to look at the state space, let's go ahead and define what a state is. So let's go ahead and define a state. Okay, so in this, so the problem is, again, I'll repeat it, from every starting location, we want to be able to find an action of moves, or we want to find an action, a sequence of actions such that from every starting location that Pac-Man could possibly be in, he eventually reaches the goal, or the goal which being that he gets to every space. So from any starting space, he is able to go to every single spot. So let's go ahead and first think about if we know from one starting spot we need to encode. So let's just given one starting location, we need to encode which squares he's visited. So that's going to be m times n booleans. So from one starting spot, there's m times n booleans. And how many starting spots are there? There's a total of m times n starting spots. So therefore, the number of booleans that we have is mn times mn, which is equal to mn squared. Booleans. So again, these booleans represent from a starting spot. If Pac-Man started in this starting spot, did he visit this spot in the board? So it's, again, these booleans represent if Pac-Man started in a certain spot, did he visit a certain spot in the grid? Okay, so this is going to be enough for us to figure out if it's going to be enough for us to solve this question. And so this is going to be solved when every single Boolean is true, which is saying that from every starting spot, Pac-Man has visited every square. So from every starting spot, every Boolean is true. So this is our state is going to be m times mn squared Booleans, but we're not looking for this what a state is. We're looking for a state size. So the state size would just basically be how many different configurations of the state are there. So since our state is represented as a bunch of Booleans, each Boolean can be true or false. So we do 2 to the mn squared Booleans, or configurations. So this is going to be our state space.